attractive in terms of views, right? And then this the song or not. And that's which I kind of skipped by actually benchmarking RNN, which surprisingly performed better than transformers for time series component. And then also use graph attention network to do network of time series prediction. In terms of large language models, I feel my current view, my personal view is that it's for computer scientists, it's a better semantic feature extraction tool. So would it do a better job than the engagement or basically topic features that we extracted back at that time? I think it's still open because a predefined vocabulary of 400,000 content features is still pretty powerful. Maybe and also disclaimers that they were generated by Google, right? There's no way that us, the university lab, can generate those. So Google can probably generate better versions of that. They probably have it in-house, just not released. Yeah, and what can LLMs do I feel like right now the setup for the last part is probably a bit too mathematical to immediately see where an LLM plugs in. But then in terms of forecasting and processing content, I think there's lots of possibilities. But if you feel free to disagree, and if you have ideas, find me for a chat.
Yeah, thank you for sharing the insights from the items to the market. So I have a quick question. So you have mentioned there is a ripple effects of the popularity. So I think it's from the explanatory view. So can we predict maybe the popularity of a song given maybe another song is hot? Yeah.
Yeah, that's a great question. So we essentially, I skip a bunch of details. Where this work, the setup, we basically set up forecasting tasks for the music video views by observing. There are two tasks that we investigated by essentially observing the history of all songs and try to do better prediction with the information from other songs. Like if I already see a spike in other songs, then can I predict the spike tomorrow? The other setting is imputation, where you pretend that one song's time series is not observed from tomorrow, but you do observe the views from other time series in the same time slot and benchmark how well that does. So the hidden secret is that we did actually two versions of the music video time series prediction. First of all, we were just doing a massive linear regression that worked actually fairly well. But I looked at that model and thought, and it was better than a small version for recurrent neural network at the time. But I basically thought Alistair Chuan, our other PhD student, had a unique knack of making large systems work. I say, you can surely do better. And he did by essentially introducing graph attention for time series prediction, which I think, that graph networks has been a really big topic in the web conference. I think that's going to continue.
Oh yeah, thank you for answering this question. Okay, I think due to the time limits, let's thank Prof. Xie again for introducing this wonderful talk. Yeah.
Thank you.
Oh, okay. So let's welcome our second keynote speaker, Dr. Xu from Microsoft Research. Let me briefly introduce the bio of Dr. Xu. Dr. Xu Chang is a senior researcher in the machine learning group at Microsoft Research Asia. Her research broadly focuses on sequential modeling with recent interest in time series analysis and generative modeling, particularly in finance and healthcare applications. She works on diffusion-based model with guidance mechanisms to improve the fidelity and depth activity of synthetic time series data, as well as cross-domain generalization techniques for better performance in data scarce settings. Here, her research has been published in so many prestigious journals and conferences, such as IEEE, TKDE, KDD, ICLR, WW, and so on, and has received over 1,000 citations. Okay, let's give her a round of claps.
Let's start. Good morning, everyone. I'm Chang Xu from Microsoft Research Asia, and thank Dr. Yuxuan Liang for the kind invitation. It's a real pleasure to be here at the web conference and to have this opportunity to share some of our recent work. At MSRA, our team mainly focus on two areas: pushing the boundary of machine learning algorithm and transforming these innovations into real-world applications. Recently, we have been particularly excited about exploring the intersection of diffusion models and time series modeling, as diffusion models has shown expressive success across modalities, including time series modeling. To address the unique challenges of temporal data in industry setting, we propose a guided learning process which brings more control, efficiency, and adaptability to diffusion models. So in today's talk, I'm going to share how we approach this problem, the strategies we found effective, and how we have developed specific methods to enable real-world applications, such as in finance and healthcare. So let's get started. What exactly is time series data? Simply put, a time series is a sequence of data points ordered by time. When we have d equals 1, it is called a univariate time series, meaning we are looking at a single variable. If d is larger than 1, it becomes a multivariate time series where we are dealing with multiple variables. And time series data is incredibly valuable because it captures how system and process evolve over time, giving us insight about the dynamics of the system. Let's take a quick look at time series data in real world. In fact, any data that depends on the past observations and changes over time can be considered time series data. It is everywhere and plays a huge role in different industries, such as finance, healthcare, traffic, and energy. For example, time series is fundamental in financial world It tracks how asset value changes over time. And stock price reflects market trend at different intervals, helping investors analyze price patterns. Time series is also widely used in healthcare. For example, ECG signals monitor heart activities continuously, helping detect issues like arrhythmias and heart disease. Time series is also essential in traffic management, energy systems, and giving us valuable insight to understand, predict, and optimize the complex system. Let's review the classical time series models. Traditional models like AR and ARIMA are simple and good for forecasting based on the past data. Classical machine learning models like random forest, gradient boost SVM, and they are more flexible and can be used for forecasting and classification and more. Deep learning models like RNNs, CNNs, and transformers, and they are powerful for capturing more complex patterns. They can cover a wide range of tasks like forecasting, generation, imputation, and classification. And more recently, generative models like GANs, Waves, and especially diffusion model have shown strong potential to go even further on these tasks. Let's look at diffusion model. In recent years, diffusion models has risen to prominence and significantly influenced various domains, including natural language processing, computer vision, and general multimodal learning. Diffusion models represent a family of probabilistic generative models that undergo optimization through a two-step process, involving the injection and consequently removal of noise across a set of training samples. This process comprises a forward price, which is called diffusion, and a reverse phase known as denoising. In a forward process, we take a data sample x0 and gradually adding very small amount of Gaussian noise to it, and then repeat this process for t steps. As the time step increase, the more features of original data have been destroyed. And in the reverse phase, we train the model to get rid of the noise added during the diffusion process. The model learns to generate effective data sample during inference that aligns closely with the distribution of training data. Here we show the derivation of a representative and fundamental diffusion model called DDPM, or denoising diffusion probabilistic model. By maximizing the evidence lower bound, we got the final loss. Actually, diffusion models are a good fit for time series modeling. Time series data can be pretty tricky because it comes with some key challenges. First, there are complex dependencies. Past values can influence the future ones in very complicated way. Then there's the issue of working in cross-domain and future setting where we might not have a lot of data from a specific domain, but we still need to make a good prediction. Finally, there's a problem of noise data and missing value. That is something may almost come up in the real world data. So this is where diffusion model really shine. The step-by-step denoising process allows them to capture both the local fine-grained details and global long-term trends. And they also have great ability to generalize to new and unseen domain, even when there's limited data available. And they're also robust to noise data, naturally handling missing values and irregular patterns through their probabilistic generation process. So overall, diffusion models are a good tool when it comes to tackling these common time series challenges. Recently, there have been many innovative works on diffusion models. These include new architecture design that combines diffusion with RNNs, CNNs, and transformers. There are also task-specific models such as CART for classification and CSDI for imputation. In addition, there are some approaches tailored to specific applications, such as ECG generation in healthcare and traffic forecasting in transportation, and so on. So our work proposed that diffusion model, when combined with guided learning process, we can form a versatile and intervenable framework for time series modeling. Diffusion models are flexible probabilistic tools. They can handle both generative tasks, where we model the full distribution of the data, and it also can conduct predictive tasks, where we focus on conditional distribution. This versatility, their flexibility makes them versatile across a wide range of applications, including forecasting, generation, imputation, and classification. But in many real-world applications, versatility is not enough. We also need the model to be intervenable, that is, being able to follow domain knowledge, meet specific objective, or handle custom constraints. That is where guided learning comes in. A guided learning process refers to incorporating additional information or constraints into the diffusion model to steer the generation or prediction process towards desired outcomes. By introducing the additional information or constraints, we can get the model learning or inference and better align it with practical needs. So by combining the versatility of diffusion model with the control from guided learning, we end up with a unified framework that is well suited for real-world applications. Here we present 3 general guidance strategies in diffusion models, and each of these strategies is designed to handle different types of guidance signals and offers its own advantages to diffusion models for controllability, efficiency, and adaptability. The first one is inductive bias. It is used when we have human prior knowledge about the task. The idea is to embed the prior knowledge directly into the model structure, which improves model performance through better inductive design. The second one is incorporating conditions. These strategies applies when explicit conditioning information is available, such as external variables or contextual cues. The model can use this information to get output and make it easier to adapt to different tasks or domains in a flexible and modular way. And the third one is gradient adjustment in sampling. Here we assume explicit guidance signals are provided. This could be objective, preference, or constraints. The model sampling trajectories adjusted using external gradients without the need for retraining. This makes it a very efficient and plug-and-play method for control. These strategies provide us with practical tools to steer diffusion model toward desired behaviors. So there are 3 key benefits of guided learning process in time series modeling. The first one is controllability. Guided learning process explicit control to steer the prediction or generation more precisely. The second one is adaptability. It helps model generalize across different domains by incorporating domain-specific knowledge, and it also supports task awareness by ensuring the model is aligned with specific goals. And most importantly, it boosts performance, delivering better accuracy, stability, and balanced trade-offs like bias and consistency. So next, I will introduce a few key efforts from our team. This slide lists some time series generation methods. TimeDP tackles multi-domain generation without domain labels. It makes use of few short samples and temporal patterns guided by inductive bias. The key benefits are controllability and strong domain adaptation. The second one is bridge. It enables text condition generation where natural language description steer the output. This leverages conditioning information, offering controllability and flexibility for domain adaptation. And the third one, DIGA, focus on financial time series guided by scenario-based conditioning, mainly to enhance controllability. And the fourth one, TARDIF, focuses on healthcare. It uses guidance adjustment in sampling guided by influence function to generate data that improves task performance. This supports better task adaptation, especially for rare and critical cases. And here are two works of our time series forecasting efforts. InfDiff is a bias mitigating framework for robust forecasting. Even when bias labels are unavailable, it uses gradient adjustment in sampling, which improves generalization and leads to better forecasting performance, especially on out of distribution data. And TSD introduces multi-granularity targets into diffusion forecasting. It uses inductive bias to improve stability and accuracy. So let's take a closer look at each of our work. The first one, TimeDP, is our framework for cross-domain time series generation. We know time series generation is valuable for real-world needs like data augmentation, privacy protecting, and scenario simulation. But most existing models only work well within a single domain, and they usually require explicit labels or conditions to generalize. This limits their stability to new domains. And TimeDP tackles this by introducing time series prototypes. Think of them as building block of time series, capturing patterns like trends or seasonality, much like word in a sentence. By composing these prototypes, the model can build domain prompts automatically. This makes the approach label and text-free, allowing it to directly learn cross-domain features from data. And more importantly, it supports few-shot generation, adapting to unseen domains using just a few samples. So let's see how TimeDP is designed to enable the cross-domain generalization. At the heart of the model are what we call time series prototype, denoted as P. These are fixed orthogonally initialized vectors that act as the basic style units of time series. It captures key patterns like trends and seasonalities. You can think of them as a kind of vocabulary for time series style, sharing cross-domain informations. Given a time series sample, the model learned how to allocate across these prototypes. This allocation M equals phi x is extracted by prototype assignment module, and they treat this as a kind of domain prompt. Then we plug this prompt into the diffusion model during training. Finally, TimeDP supports few-shot prompting, and users can simply provide a few example time series, and the model automatically extract relevant prototypes. And here we show some examples generated by TimeDP. On the left, we input some examples from electricity, rain, and traffic time series. TimeDP extract key patterns and use them to get the generation process. On the right, you can see it generates diverse and realistic samples. And here we highlight the superior generation performance of TimeDP. First, TimeDP deliver state-of-the-art results across 12 real-world data sets from 4 major industries: energy, transportation, weather, and finance. And second, it shows strong few-shot generalization. Even with just a few examples from an unseen domain, TimeDP outperforms all the baselines. And third is realism improves with more few-shot samples provided. Here's our second work. Bridge is a framework that uses text as a form of guidance to control time series generation. Text can carry rich semantic meaning, domain knowledge, and even instance-specific signals, which makes it a powerful conditioning source for generating meaningful time series data. But it comes with a few key challenges. First, there's a lack of high-quality paired data between text and time series. And second, it is non-trivial to bridge the modality gap between language and numerical sequence. To address these challenges, Bridge introduced 2 main innovations. We propose a multi-agent framework based on LLMs and automatically synthesizes diverse and realistic text-to-time series data sets. And we also design a hybrid text condition generation framework that combines semantic prototype with free-form text descriptions, allowing both structured and flexible domain-level control. Here's a framework of our model. Bridge model consists of 2 main stages. The first one is text-to-time series preparation, and second one is text control time series generation. And the first stage consists of 3 steps: collecting time series related text from online sources and extract initial text template. And second one is performing automatic evaluation to assess the quality of generated descriptions. And the third one is employing a feedback-driven refinement process via a multi-agent system to iteratively improve the textual outputs. And through this pipeline, we construct high-quality text-to-time series data sets. And in the second stage, a textual description is combined with domain-specific prototypes and their weights, that is, domain prompt. And the fuse input is used to condition the diffusion model for text control time series generation. So this slide shows an example of generated text and how textual input is used to guide time series generation in our framework. We analyze the structured text description, which is divided into 3 levels of details. The first one, we see general background information. It tells us that the data comes from which data set and what task it is used for. And next, there's a general description of statistical properties, mentioning the time window of 168 steps and fluctuation range from 2 to 74. Finally, we have specific semantic and structural requirements, such as an overall ascending trend and a significant peak at time step 46. And this hybrid textual prop is fed into our bridge framework, and the output synthesis time series reflects these textual conditions. We can observe the upward trends and a noticeable peak exactly at the 46 time series. Experimental results confirm that textual description significantly improve both accuracy and semantic controllability of the generated time series. across 12 real-world datasets, model condition on text consistently achieve lower MSE and MAE, indicating improved assignment with the target series. And additionally, we observe higher score in human evaluation metrics of bridge. Now, let's take a look at TARDIF, our third piece of work. The main idea behind TARDIF is that just generating data that looks like real thing is not always enough. Most generation methods try to match the original distribution, but that often means common patterns dominate, and rare but important cases get ignored. TARDIF proposes to make generation task-aware. We introduce influence-guided generation, where we get a diffusion process using influence function that measures how useful a sample is for improving a downstream task. In other words, we generate data that actually helps the model do better on the downstream task. We apply this especially to healthcare, generating realistic electronic healthcare record time series for critical tasks like mortality prediction or rare disease diagnosis, where data is often limited but critical. Here's the algorithm of our influence-guided generation. We assume how much a training sample helps downstream performance. And during the diffusion sampling, we get generation towards samples with higher influence so that we generate useful and not just realistic data. We achieve this by incorporating gradient adjustment during sampling process. And we tested on 6 medical datasets covering tasks like ICU stay prediction and rare disease diagnosis. Compared to other baseline methods, TARDIF consistently generate data that leads to better or comparable downstream performance, sometimes even outperforms real data. And next one is MGTSD. It is a multi-granularity diffusion model designed for time series forecasting. One challenge with using diffusion models in forecasting is the randomness during sampling. It can lead to unstable or low fidelity predictions. MGTSD tackled this by introducing multi-granularity guidance. We observed that time series data often have natural structures at different levels, from fine grain to coarse grain. The process of smoothing data from finest grain to coarsest grain naturally aligns with the diffusion process. So we use different granularity as intermediate targets during the diffusion process to get the learning in a more stable and meaningful way. Let's quickly touch on how we apply multi-granularity guidance. We introduce multi-granularity guidance by supervising both intermediate and final state during diffusion, and using the cost-to-find targets and combined laws to encourage more structured and stable generation. Here's the performance comparison on 6 real-world data sets using CRPS, which evaluates both accuracy and uncertainty of probabilistic forecasting. We can see that MGTSD consistently outperforms other baseline models, achieving the best performance across all data sets. And this demonstrates the effectiveness of our multi-granularity guided learning model in improving both stability and prediction quality in time series forecasting. Next is InfDiff, a framework that is designed to address bias in diffusion models. Since diffusion models are highly data-driven and they can easily inherit biases from real-world data set. InfDiff addresses this by adjusting the sampling gradients using event learning techniques, getting the model towards more balanced outcomes, all without relying on extra bias labels. And this is the last one of our work, DIGA, a diffusion-based framework for financial market simulation. DIGA models the market by capturing key dynamics like mid-price, return rates, and order arrival rates using a conditional diffusion model. On top of that, it introduced a meta agent with built-in financial knowledge to generate realistic and controllable order streams. This approach improves both fidelity and controllability of the synthetic financial data, makes it more useful for downstream tasks like strategy testing or market modeling. And finally, there's one thing I'd like to share. We have integrated our time series generation works into a unified framework called TimeGen, which we plan to open source next month. So please stay tuned. To wrap up, here's a quick recap of what we have covered today. We started with the foundation of time series modeling and explore how diffusion models are bringing fresh capability to this domain. And we look at a key guided learning process, such as injecting inductive bias using conditional input, and even applying gradient-based adjustment during sampling to make generation more task awareness. And then we walk through our model innovations, including TimeDP, Bridge, TARDIF, and DIGA, and forecasting models like MGTSD and InfDiff, each of these addressing different challenges in time series generation and forecasting. And we also show how these approaches have real-world impact, especially in finance and healthcare. So that's all of my part. And thank you all for your time and attention. So if any part of today's talk inspired you, sparked your interest, I'd like to chat more. Discussions and collaborations are always warm welcome. And we're also hiring research interns. So if you are curious or interested, please do not hesitate to contact me. So that's all. Thank you.
Okay, thanks, Dr. Xu, for sharing a series of wonderful talk on time series generation based on diffusion model. So if you have question, please raise your hand.
Hi, thank you very much for your insightful presentation. And I have a quick question about the time DP. Is that the name of the model? I'm just curious about what if the time series do not have very clear seasonality or the clear trends, does this model can still capability to learn the representation?
Yes, thank you for the question. Actually, TimeDP relies on the prototypes, which we propose to capture the underlying seasonality or trend of the time series data. We don't explicitly extract those trend of seasonality features, but we use the domain prototype to capture them automatically. Actually, the prototypes we propose is just like word in a sentence is the most basically element in the time series data. So as we conducted a series of experiments across multiple data from different industries, we found that it can extract and capture the cross-domain information very effectively. So I think it can conduct the prototype extraction automatically, even if they are not explicit but implicit features.
Thank you very much.
Thanks for your interesting talk. Your team has done very systematic research on this diffusion model on time series generation. Yeah, and I have learned a lot from you. My first question is for the MGTSD, the iClear 2024. Yeah, I think I have missed some details. Like, how does this method supervise both immediate representation and final prediction?
Thanks for the question. And actually, the algorithm is a little bit complicated. The basic innovation behind our work is that the process of smoothing data from fine-grained to coarse-grained naturally aligns with the diffusion process. So you can see, like this picture, a time series data can have many different granularities, and the diffusion process looks like the same. They have noise data and gradually removal of the noise data to a clear and fine-grained form. And we use this intuition inside the diffusion training process. Here's the detail, but it's a little bit complicated. Actually, we introduced coarse-grained targets at the intermediate diffusion steps. It looks like if you have T-step, if you have 100 steps of denoising steps, and if you have a coarse-grained data, it may look like in the middle of the diffusion process, maybe at about 1,500 steps, and the intermediate state of diffusion model may look like the fine-grained data of that time series data. So you can use the time series coarse-grained time series data as an intermediate guidance signal to guide the learning process.
I see. Thank you. And my second question is, I noticed that the baselines of time series generation are almost GAN or VE based methods. And I have already known from your talk the benefits of diffusion models on time series generation, like controllability, adaptability, and performance. Can you share some insights on its limitations compared with traditional like transformer or MLP-based methods?
Well, it's a very good question. And actually, diffusion models has shown impressive success across modality, and recently many SOTA works, maybe in natural language processing or computer vision, their SOTA models are all diffusion-based models. I think diffusion models have great ability in capturing complex patterns and have great modeling ability. So as we shown in our experimental results, their performance on controllability and generation quality are relatively good compared to those traditional methods. But I think maybe diffusion model is not as good enough traditionally methods as their efficiency in computation, or maybe some quality in interpretability. So I think that may be the limitation of diffusion-based models compared to traditional methods.
Okay, thank you.
Okay, due to the time limits, we may have the last question. So who is the lucky one? Okay, I may be the lucky one. Okay. Yeah. Thank you for introducing so many works. So I think there are 6 models within this slide. So is it possible maybe to integrate all of them into one, maybe one fit all, such kind of framework? Yeah.
Oh, that's a very good question. Actually, we have conduct different efforts on time series generation and improving the prediction performance. And as diffusion models are powerful models for a lot of tasks like prediction or generation, it is possible maybe in the future to integrate those works together. But currently we have only integrate the three models for time series generation into a unified framework to provide more controllability and efficiency and cross-domain generalization to time series generation tasks. So it will be released maybe next month.
Oh, yeah, that's great news. Maybe we are looking forward, maybe a foundation model that is based on a diffusion model, yeah, instead of maybe based on transformer, yeah.
Okay, we can discuss it further, and hopefully we can have a maybe good idea to push this idea more in the future.
Yeah, looking forward maybe to further collaboration. Yeah, thank you.
Thank
Okay.
you.
Yeah, we just completed the first half of the morning session. Yeah, let's enjoy maybe a 20 minutes coffee break, and then we can gather together for the second session, second half of the morning session. Yeah, thank you. Okay, maybe we can get started for the second half. Okay, after the 2 keynote speech, so we will have the second half of the morning schedule. We have 6 full papers for presentation. And the first one is graph stage channel preserving graph neural networks for time series forecasting. And the speakers are from online. I will change to another view. Okay, Tom, can you hear us?
I can hear you.
Okay, so you can get started.
Okay. Thank you, Vishal. Can you see my slide?
Oh yeah, so can you maybe increase the voice? Sorry, we cannot hear you. Yeah, maybe wait a minute.
Can you hear me
Sorry, so how can we share the audio?
now? Can you hear me? Excuse me. Can you hear me?
Sorry, Tom, please wait a minute.
可以让别的
Okay.
presentation 往上第二个可以我得去问一下那个 staff。
Okay. Oh yeah, sorry, Tom. So we
Can you-
need maybe more time to figure out. So maybe we switch you to the second one. Is it acceptable?
Okay.
Oh yeah. Thank you for your understanding. Okay. Maybe we will first have the second speaker. Let me see. Okay. The paper is Mamba continuous state space modeling with dynamic graph. Okay. Let's invite our second speaker from the University of Tokyo. Yeah. Oh.
This one what？我有那个，这里有 mute 一下。我有 mute 这个，等一下。
Thank you to the WebST organizers for giving us the opportunity to present our recent work on dynamic graph modeling. This work is collaboration among 3 institutions, and I would like to start by expressing my sincere gratitude to all of my collaborators. In today's presentation, we will cover 5 main parts. First, the background. What is dynamic graph modeling? Second, the motivation. Why we introduce Mamba into dynamic graph modeling. Third, the methodology. How we design our framework to address key challenges. First, our experiment results, and finally, the conclusion. First, we introduce the definition of dynamic graph modeling. Dynamic graph modeling aims to learn node or edge embeddings by leveraging both structural and temporal information from dynamic graphs. In real-world scenarios, there are 2 types of dynamic graphs: discrete time dynamic graph and continuous time dynamic graph. Discrete time dynamic graphs partition the dynamic graphs into a sequence of snapshots based on the causal grain time intervals. However, compared to continuous time dynamic graphs, they lose fine-grained temporal information, which often leads to suboptimal performance on tasks that require high temporal precision. Therefore, this work focuses on modeling continuous time dynamic graphs. The overall process of dynamic graph modeling consists of 3 main steps. First, the dynamic graph is taken as input. Second, the model learns representations for dynamic graph. And finally, these representations are applied to various downstream tasks. Among these steps, dynamic graph representation learning plays the most critical role, as the quality of learned representations directly determines the performance of downstream tasks. To learn high-quality dynamic graph representations, many successful architectures have been proposed, including GNNs, RNNs, MLPs, and transformers. Among them, digiformer, which leverage transformer architectures, have achieved the best performance so far, because it can capture long-term sequence dependencies. Specifically, earlier GNN and RNN-based methods suffer from poor performance in modeling long sequences due to the vanishing gradient issues. Digiformer addressed this by introducing transformer structures along with a patching technique, enabling it modeling much longer input sequences and achieve significant performance improvements. However, a major limitation of digiformer is that the complexity of its self-attention mechanism grows quadratically with input size, which becomes a serious bottleneck when modeling large-scale dynamic graphs. Recently, work from computer vision field, such as Vision Mamba, has shown that Mamba architectures can outperform transformers in long sequence modeling tasks, while maintain only linear computation complexity. Inspired by these findings, we asked the following question: can we introduce Mamba framework to efficiently handle dynamic graph modeling? We then conduct a preliminary experiment on 4 representative frameworks: MLP, graph mixer, an RN-based model, TGN, a transformer architecture, digiformer, and the vanilla Mamba. In this experiment, we compared the original method, which used temporal information, with versions where the temporal information has been removed. In the figure, the purple bars represent the original models with using the time information, while the green bars represent the models without time information. We observe that current methods, including vanilla Mamba, show only a slight performance drop when time information is removed. This suggests that existing methods may not fully leveraging temporal information. Mm, sorry. Oh. uh, mm. Due to the challenge posed by irregular time intervals, which makes it hard for them to effectively utilize time information. Based on this observation, we raise an question: how can temporal information be fully utilized to improve the effectiveness of dynamic graph modeling? And can Mamba framework address this challenge? Now, we also conducted another preliminary experiment on the same four frameworks, MLP, RN, Transformer, and Vanilla Mamba, using two different testing settings on Enron dataset, the transductive and inductive settings. In transductive setting, all nodes in the testing phase have already been seen during training. In contrast, the inductive setting involves testing on nodes that were not observed during training, which allows us to evaluate the model's generalization ability for unseen nodes. We observe that current method experiments a significant performance drop in the inductive setting, indicating poor generalization for unseen nodes. Based on this observation, we raise another important question: how can Mamba enhance model generalization for capturing long-term dependencies in dynamic graph modeling? Next, we introduce how our method addresses the above-mentioned three challenges. First, let me briefly introduce state space models. As shown in this figure, state space models have two core components. To convert a continuous SSM into a discrete one that we can use, we need to define two core components, the step size t, and the state updating parameters bar A and bar B. To improve modeling efficiency, we propose Mamba as a superior alternative to transformer architectures for dynamic graph modeling. From our preliminary experiments, we have observed that the Vanilla Mamba also face these two problems. So we redefine the co-parameters of Vanilla Mamba, the step size and the state updating parameters to address these problems. Specifically, to improve effectiveness, we set the step size t as a time interval dependent variable, allowing the model to better leverage temporal information. Compared to the original Mamba, which defines t as a function of the input sequence, we instead define t as a function of time steps. By making the step size directly dependent on time steps, our model can better capture irregular time intervals inherent in dynamic graphs, providing a more accurate temporal embedding. This design is theoretically supported by Theory 2 in our paper. The key insight is that the change in node representations depends on the time intervals rather than on input variables themselves. So finally, to enhance generalization, we set updating parameters bar A and bar B as time-dependent variables. In theory 3, of our paper, we theoretically prove that time-dependent variables can reveal how time intervals influence representation changes, enabling better representation prediction for unseen nodes. Compared to Vanilla Mamba, where the updating variable A bar and B bar are defined as input-dependent functions, our approach addressed an important limitation. In Vanilla Mamba, when the model encounters new unseen node during testing, the reliance on input-dependent variables significantly decreases performance. To overcome this, we define bar A and bar B as function of time intervals. This allows the model to adjust the strength of node representation updates based on the size of the time intervals, even for unseen nodes. Next, we present the mean experimental result from our paper. As shown in tables 1 and 2, our proposed Daiji-Mamba framework achieves state-of-the-art performance, demonstrating that the Mamba architecture can effectively capture long-term dependencies and improve the link prediction tasks. In table 3, we present ablation studies. When removing either time encoding or time span component, the model's performance drops significantly. This confirms that the improvements are indeed due to better utilization of irregular time information. Furthermore, as shown in figure 1, we conduct additional ablation studies to investigate the model's generalization. We observe that when we remove time span dependency, that is, when the state updating parameters bar A and bar B are made input dependent again, similar to vanilla Mamba, the model's performance in the inductive setting drops significantly. This result further supports that defining updating variables at time interval dependent enhances model's generalization ability. Finally, we provide an analysis of the model's efficiency and robustness. As shown in figure 1, compared to state-of-the-art dynamic graph modeling frameworks, Daiji-Mamba achieves clear advantages in both model size and performance, demonstrating its efficiency. As shown in figure 2, while transformer architectures suffer from quadratic time complexity, Daiji-Mamba maintains linear time complexity in both runtime and GPU memory consumption, further validating its efficiency. As shown in figure 3, Daiji-Mamba achieves better performance when modeling longer sequences, highlighting its strong ability in long sequence modeling. Finally, as shown in figure 4, Daiji-Mamba consistently achieves the best performance, even on noisy graphs, showing its robustness. Finally, we conclude our presentation with the main findings of this work. First, Mamba frameworks enable more efficient and more effective modeling of dynamic graphs compared to other architectures, such as GNS, RNNs, and transformers. Second, making the step-set T dependent on time can better leverage time information to improve models' effectiveness. Exploring more suitable time interval functions is one of our future research direction. Third, making the update parameters bar A and bar B dependent on time intervals indeed improves models' generalization ability. Finally, we provide our code on GitHub and paper, and also my personal contact information. Thank you very much for your attention.
Okay, thanks to Dr. Li for sharing this insightful work. So do you have any questions? You can raise your hand. I will pass the microphone to you. Okay, I have a quick question. So could you please go back to the conclusion part? Yeah, you just introduced how to leverage the Mamba for considering the time interval between maybe between the dynamic graphs, right? So I didn't really understand how to process maybe the spatial correlation between different nodes. Still using Mamba or any other architecture here?
Thanks for your question. It's a good question. So currently, long-term dependency modeling architectures actually don't use the structural, the deep structural information. They just use the first hop neighborhood sequences. So that's an issue that we need to solve in the future.
Okay, so how to combine maybe the information from the locality? Just using a maybe graph neural network or any other approaches here?
Yeah. that will be a good way, yeah, to use some graph neural networks to extract the deeper structural information and combine with the sequence information. Yeah.
Okay, and another question is regarding the time interval. So if the time interval between maybe two adjacent frames is really large, so what is the effect maybe on the bar A and bar B?
Mm. Mm. Oh, thanks for your question. Yeah, the bar A and the bar B determine the updating rule for the variables. So it indicates that the longer time intervals, we should forget more historical information and update by considering the new input. So the bar A and the bar B can do this.
Oh, okay, I see. So if the time interval is larger, so we should have some decay over the previous hidden state.
Yeah.
Oh, okay, that's a good point. Okay, thank you for your
Thanks for your
explanation.
question very much.
Okay. Okay, maybe let's move on to the second speaker. So let me see. The paper title is work smarter, not harder, towards efficient and effective route travel time estimation framework. Okay, and for this paper, we have a proxy speaker. Yeah, please go.
Okay, good morning, everyone. On behalf of the first author, and I'm today here to share the paper, Work Smarter, Not Harder towards an efficient and effective in-route travel time estimation framework. And, yes, travel time estimation and also TTE in short is crucial for intelligent transportation systems like route planning, navigation, and ride hailing. And in our work, we will talk about en-route TTE. The definition is predicting the travel time of the remaining route according to the traveled route information as shown in the left figure. However, developing an efficient and effective in TTE framework faces several challenges. The first one challenge is how to reduce the number of invoking estimation models without the loss of accuracy. And so to improve timely navigation updates, ERTTE must refresh remaining travel time estimates during the route. And however, frequent model invocations cause delays due to the inference time and high concurrent user requests further strain the system capacity. And we also have a challenge two is how to ensure the robustness of the TTE model throughout the route. It's essential to balance the general driving patterns with route-specific conditions, and the model should learn common travel patterns across routes. We are also quickly adapting to individual driving styles, such as unique acceleration or braking habits. Additionally, it must promptly adjust to unexpected conditions like traffic congestion or accidents to deliver accurate real-time predictions. Yes. And so based on these challenges, And this paper, as is shown in the figure, our insight is, well, the system first quantified certainty across the entire route and stores confidence intervals. And during travel, it monitors accurate travel time. And if the travel time remains within the confidence intervals, the estimate is retained and avoiding unnecessary re-estimations. And only when significant deviations occur, indicating changed traffic conditions, does the system trigger re-estimation. So according to our insight, we propose a general efficient and effective framework called ERTTE, and it combines two novel components: uncertainty guide, that's uncertainty guided decision, also UGD in short, and to address the challenge one, and fine tuning with meta learning, and to address the challenge two. And well, the goal of UGD is to improve efficiency by deciding intelligently when to do re-estimate, and the uncertainty guide decision process is categorized into two distinct phrases: pre-route phrase and en-route query. Initially, in the pre-route query phrase, the trained backbone model is utilized to compute the confidence intervals for each route prior to departure, which are then stored in the TTE database. And subsequently, in the en-route query phase, these confidence intervals are employed to verify the accuracy of ongoing prediction. And in the right is the details of the UGD algorithm. During the en-route query, if the actual travel time deviates from the established confidence intervals, indicating the necessity for adjustments, the model is invoked to re-estimate the travel time for the remainder of the route, and then updating the corresponding confidence intervals in the TTE database accordingly. And then if the current predictions fall within confidence intervals, the existing estimations are retained to respond to the en-route queries. Notably, the key point is to calculate, store, and update confidence intervals due to the confidence intervals provided a solid foundation for decision making. And then to accurately supervise the predictions and the corresponding confidence intervals, we employ quantile regression, which is a robust and effective method for quantifying uncertainty. Quantile regression is distribution-free and directly optimizes the quantile loss function for providing precise supervision on specific quantile values without requiring any external parameters. The equation shows the details of quantile loss, and we use different quantile values to supervise low bound, mean value, and upper bound. And so the goal of the fine-tuning with meta-learning, FTML in short, is to enhance model robustness, that's to learn general patterns and adapt quickly. So inspired by MAMO, which is a famous meta-learning algorithm, and FTML comprises two stages: the pre-training and fine-tuning. Well, in the pre-training stage, we learns general driving patterns by predicting both the entire route arrival time and the travel time at the specific locations, along with their confidence intervals. The model parameters are updated to enable the model to learn general driving patterns. in the fine-tuning stage, according updated weights parameters, the model further adjusts by predicting the travel time and the confidence interval for the remaining, enabling it to adapt to real-time conditions. Yes, for the experiments, we choose two real trajectory data set, Porto and Xi'an, and we choose two types of baselines, TTE method and the ERTTE method, as is shown in the right figure. We also compare with two strategies that can improve throughput. First one is the random. That's all samples are not specially processed and are first come, first served. And the second is a greedy strategy that to predict the longest routes first, and since they are not since they are the hardest to estimate. And more important, we show the efficiency of our framework. The left is inference time comparison between UGD and without UGD algorithm, and the right one is the throughput. Our framework could improve both inference speed and the throughput. We also conduct scalability experiments and ablation studies to demonstrate the scalability of our framework and the effectiveness of the components in ERTTE. And for the online test, this figure shows the relationship between travel time and route completion percentage for two routes in Xi'an city. And the left chart, as we can see, only 3 requests required reestimation due to holiday travel and initial acceleration phases, causing deviations from the predicted intervals. And the right chart, we can see the late night travel showed stable traffic conditions requiring no reestimations. So our framework ERTTE efficiently adjusts to varying traffic conditions, triggering reestimations only when necessary, and ensuring both flexibility and efficiency. Thanks for your listening, and here's the homepage and the QR code of this work. And if you have any questions, you could write emails to the authors, and also could scan the QR code and WeChat to follow authors' this official accounts to get more information about spatial-temporal data mining. Thank you very much.
Okay, thanks, Xizhen, for presenting this paper. Since this is a proxy presenter, so we may leave our QA session, maybe drop an email. Okay. And for the next speaker, so it is from online. So I would switch to the Zoom session. Yeah, hi, Tong. Can you hear us?
Yes, I can hear you.
Okay. And okay,
So please get started.
Hi, dear PC Yuxuan, can you see my slide?
not really. Maybe a little bit delay. Oh, yeah. Okay, now, so we can see your screen.
Okay. Can I get started?
Yeah, we are enlarging your volume.
Okay. Can I start?
Yeah, it's okay now. Yeah, please get started. Yeah.
Okay. Thank you, everyone. Hello, everyone. Good morning. I'm Guan Tong, currently a joint PhD candidate of Zhejiang University and Griffith University. It's my great pleasure to share my recent work supervised by Prof. Shri Pan with you on the WebST workshop. This paper is titled with Graph Stage Channel Preserving GNNs for Time Series Forecasting. Actually, in this work, we study a typical problem, time series forecasting. It's a general topic in recent 3 years, but we found that there's something unexplored. This problem can be formulated as this, and the f theta is the model we constructed, and x is the input series with input length t, and y is the prediction object with output length k. The problem recent study in this field mainly focus on the core challenge of learning dependencies, especially intra-series dependence, inter-series dependence, and cross-series dependence. And we summarize the large number of recent study as channel mixing methods and categorize them to system 1 and system 2. For the system 1, they potentially overlook the kind of dependence because they mix the either the node dimension or the time dimension with the hidden layer dimension, which is shown as such as for the inter-series only model, such as I-transformer, they project the original input with dimension n multiple t into the hidden layer with dimension n multiple d, and the original time dimension t is disappear. And for the channel system 2, they try to capture all 3 kinds of dependencies, including cross-series dependence. They projecting the input into a hidden layer with dimension nt multiple 1. Actually, this kind of methods treat the multivariate forecasting problem as a extremely long univariate series. So they construct a hypervariate graph with dimension nt multiple nt to extract the correlations. Okay, both of them have some weakness. For example, system 1, they tend to overlook certain dependencies. They failed to learn the underlying maybe spatial or temporal dependencies. As for the system 2, the excessive correlation extraction can take 2 potential issues. The first is increase the computational complex, and the second is a high risk of introduced potential noise. This kind of noise comes from the use of the hypervariate graph I mentioned above. This graph can give the model a broader flexibility to learn numerous connections, and these connections maybe contain some pseudo connections and diminish the weight of truly useful inter-series or intra-series dependencies, and result in first overfitting and second decrease the performance of prediction. So this raises a crucial question. Is it really necessary to model all these dependencies? So we start from the crucial question and reflect on the extraction of dependencies in current models, and emphasize that the trade-off between the variety of dependence extracted and the potential issue has not been fully explored. So we propose a model called graph stage, enable more accurate and robust dependency learning. It's a fully GN-based model. So it has a better interpretability, and we use a channel prism strategy, which lead to a more effective solution, and we decouple the learning of inter-series and intra-series dependencies. So it's an efficient model also. Okay, let's go to the methodology. You can see the overall structure is very simple and straightforward, which is combine the three key components. The first is the embedding layer, and the second is stage block, and the third is the projection layer. And for the stage block, we do the intra-series dependency extraction first, and then inter-series dependency extraction. It's a sequential structure, and in each of them, we use a learnable graph. For example, in the intra-series dependency learning module, we use AT, which is also called the temporal learnable graph. And this graph can be directly visualized to show us how the model works, how the model learns the dependencies. So we do the temporal dependency learning first, and the spatial second. So I also think this method is really corresponding to the theme of our workshop. Regarding the channel preserving, you can see many indications such as this, and this to indicate the information flow dimension. And you can see in here we preserve the node dimension and time dimension P in all of the model. So we also do some novel design in the embedding layer and stage block, which can be found in full paper. And for the experiments, we did comprehensive experiments from three aspects. The first, overall prediction results, and the second, model analysis, and third, we did some case studies. And for the overall prediction performance, we compare with some well-known baselines such as I-transformer, times-night, and something else. And we also compare with for advanced GNNs and some famous recent SOTA such as times mixer, cycle night. And we do some model analysis to claim where our performance improvement stem from. So we do some ablation study on the embedding and patching layer, and ablation on the dependency learning mechanism, and we conduct a model varied comparison to claim our framework, our decouple mechanism, our channel preserving strategy is effective and efficient. And for the case study, for example, in the part A, here is a random visualization of temporal learnable graph, AT. In the middle graph, we can see if we input 4 days of data. In the AT, you can find the 4 peak, which means the learned correlation is perfectly matched with the daily periodicity of the original input data. And for the spatial learnable graph, you can see there are some bright spot and some dark spot. The bright spot means the high correlation, and the dark means low correlation between those. And as for the high correlation nodes, we can see the pattern is same, and the low correlation nodes, the pattern is different from the others. And the part C is a case study for visualize the prediction performance across models on PAM07 dataset. We can see the graph stage can perfectly follow the trend of the ground truth data. Since I'm unable to attend the conference in person, I'll briefly introduce myself within a slide. When I was a rookie PhD, I do a lot of research in urban prediction, which is maybe related to the organizers or the general chair, program chair of our workshop. And in this work, in this graph stage, I don't limit the research scope to traffic, but explore it to maybe weather data, financial data, electricity data, and health data. And recently, we are doing something about time series intelligence. We hope time series pattern motion can be easily used as a LLM. You input a series, you input a question, and you got something you want, and it's easily to read. Thank you for your listen. And if you would like to communicate with me, please feel free to email me. I'll be very delighted to connect with you. Thank you for your precious time and effort. That's all.
Okay, thanks to Tom for the sharing. So any questions from the audience?
Thanks, Tom. You can hear me, right? So I have a question about actually study about the temporal learnable graph and then spatial learnable graph. It seems this is the best from your action study. Can you share more insights about why we should do this temporal first and then spatial?
Okay, it's a good question. So we use some compression experiments to claim this. For example, the origin is the original graph stage. It's the structure of our model. So we do the temporal first and the spatial second, and the variant A, we change the order of these two components. We do the spatial first and the temporal second. And in variant B, we use a parallel structure and we add both of them to get the output. And variant C is a kind of channel mixing strategy, not related to your question. So we use experimental comparison to find that current structure is the best. So I think maybe if you use the temporal dependence as already be extracted or learned, it will filter a lot of unrelated information, or filter a lot of maybe potential noise. So you do the temporal first, and then you do the spatial correlation learning. You will get a more accurate effective prediction result.
Yeah, thank you for sharing.
Thank you for your question.
Okay, Tom, so if no more questions, oh yeah, we still have another question. Yeah, that should be good.
Hello, just a quick question. I think slide 2 or 3, you were showing the overlapping of what your model can do. And there was one just called solar. Could you just clarify what you meant by that? Did that mean like sun data, or what exactly did that mean?
Sorry,
If you
sorry,
keep going,
speaker is not very clear.
hello,
Sorry,
can you hear me?
microphone is not very clear. Can you repeat?
Sure. If you keep going back, I'll tell you which slide to stop on.
Uh,
It was
maybe
one of
which
your,
slide?
yeah, keep going back. It was one of your first slides that you showed. You were showing a spider graph about what your, yeah, this one. Sorry, can you go back?
This one?
No, the next one. Yeah, here. You're showing all the different things that your graph stage can do, and the bottom left is just called solar. And I just want to know what exactly that means.
Okay, what's your question?
My question is, what do you mean by solar? What exactly is that information that you're taking into consideration?
Uh, mm, sorry, I don't understand your question. Could you please repeat again?
Oh, okay. So the questioner is asking what is the solar there? So you have traffic, weather. So what is solar there? The definition of the solar in the figure.
Oh,
Yeah.
okay. Okay. You mean why the performance of graph stage is pretty good in solar?
Yeah. That's the question. Yeah.
Oh, okay. Actually, I think um, the model performance is really related to uh, the original character of the data set. So in the solar data set and uh, PAMS data set and weather data set, this data set both have a character is they have a lot of nodes, not only 7 nodes, but they have maybe 700 nodes, 100 nodes. With a lot of nodes, they will, if you extract the spatial correlation, you will get more useful informations and lead to a more accurate prediction result. Actually, the performance of our model is, I think, is better in PAMS dataset because the PAMS dataset has the much larger number of nodes, which also shows the potential or the chance of use our methods in real world large scale spatial temporal forecasting task. And and also the performance in solar energy is also good. But I think in PAMS dataset, we got a much better performance.
Okay, thank you for the explanation. Let's move on to the next speaker. Yeah. Okay, so for this presentation, so we still only have the proxy presenter. Yeah.
Oh, hello everyone. My name is
Yeah. Oh, okay. So you can switch to this view. So you can.
Oh.
Yeah, I think it's okay.
Oh,
But it's not sharing. Oh, it's not sharing. Oh, yeah. So sharing is here. So you can directly use this one. You share the screen too. Yeah, I think it's okay now.
Okay. Relax. Okay. Hello, everyone. My name is Xiao Liu. I'm here to present the paper on behalf of the authors, since they cannot attend this conference. Today, I'm honored to present our recent work titled GRL for AOI, Graph-Based Reinforcement Learning for Service-Aware AOI Segmentation, in collaboration with colleagues from CMU, Beijing Jiaotong University, and Cainiao Network. Okay, the AOI, the area of interest, abbreviated AOI, segmentation is a crucial process in the location-based services, such as food delivery, ride sharing, and logistics. It aims to partition urban spaces into non-overlapping regions. The AOI segmentation can support to optimize dispatch demand for requesting and the service time estimation. Effective AOI segmentation significantly improves the operational efficiency of these services. Existing AOI segmentation methods can be categorized into three methods. The first is the fixed shape method, and the second is road network based methods, and also with the optimization based method. Each approach has its merits, but they still fail to address some challenges. To be specific, fixed shape methods disregarded important geographic and service semantics, and the road network methods fail to address specific service requirements. About the optimization based method, the optimization-based approaches are limited in feature integration and generalizability. So these shortcomings motivate the need for a more effective and sophisticated approach. And our goal is to explore a better way to address the service-aware AOI segmentation. So our contribution can be summarized as follows. First, we aim to overcome these limitations by proposing the first ever graph-based deep reinforcement learning framework named GRL for AOI. This is designed explicitly for AOI segmentation. And second, based on this framework, we propose GRL AOI L for AOI segmentation in logistics services. It adopts a value-based model DQN, deep learning reinforcement Q-learning network to improve the trajectory modularity and predictability for service in logistics. And also, we conduct extensive experiments, and the results demonstrated the superiority of our method over other baselines. Okay, let me introduce our detailed method. Our framework utilizes a detailed geographic data, such as road networks and comprehensive service data, including order and trajectories. These combined input forms the foundation for our graph-based modeling and learning. So two key questions guide our research. First, how can the deep reinforcement learning can be generalized to the problem of AOI segmentation effectively? And secondly, how can the framework flexibly accommodate multiple service goals? Okay. Let's talk about how to solve the first problem. Here is our proposed framework. GRL for AOI consists of two main stages. The first is the item region graph construction, and the second is the reinforcement learning based AOI segmentation. The the item region graph construction is used to segment the urban area into non-overlapping atomic regions, and the RL-based AI segmentation is where these atomic regions are combined sequentially, guided by a reinforcement learning agent. Okay. We first use one image-based segmentation method to identify item regions by considering fine-grained road networks as region boundaries. The AR graph, the item region graph is associated with abundant spatial-temporal features, where each node denotes a region, and each node and the nodes feature includes 3 elements. The first is the number of the parcels in the item region, and the second is the initial AI assignment by the coarse-grained rows network segmentation, and the third element is the size of the item region. Also, for the edge feature, we calculate the number of trajectory transitions between 2 adjacent item regions, allowing the model better to capture the trajectory transfer patterns between the two adjacent regions. We frame AOI. We can frame the AOI segmentation as a sequential decision making problem, where an RL agent iteratively decides the assignment of border nodes based on the current AOI segmentation state. So let's talk about how to solve the how to generate the deep reinforcement learning to AOI segmentation. The sequential decision-making problem can be represented as a Markov decision process. So we need to define the state, the actions, and the rewards. The state is defined by current segmentation and the node features. And the action involves node merging decisions. About the rewards are tailored according to the server's semantics. So specifically, the state contains 4 information. The first information is the target node information, and the second element is the neighbors of this target node. Also it includes the current AOI segmentation and the item region graph. These elements is our state. About the service-aware reward, we consider 2 primary service objectives. The first is the trajectory modularity, and the second is the predictability. The first objective, the trajectory modularity, is used to ensure the dense internal connections within AOIs. In logistics service, couriers usually finish all tasks in one AOI and then head to another one. To this end, we hope that within each AOI, there are dense trajectory connections. While between different regions, trajectory transitions are as weak as possible. So we use the ratio of the number of the trajectory completed in one same region to the number of all trajectory to calculate the first objective. And about the predictability, this goal is to achieve a better predictability of the delivery demand by appropriate AOI segmentation. Intuitively, the predictability should be tested by evaluating a given prediction model, usually deep learning models, using metrics such as MSE or RMSE. However, this model-dependent way requires retraining the prediction model each time, which is very time-consuming and practically intractable. So to tackle this challenge, we use the autocorrelation function, abbreviated ACF, to represent the predictability of an AOS time series. These two objectives shape our overall reward strategy with weights K1 and K2. And for the DQ network, we employ the graph convolutional networks to capture spatial correlations in the data, and an attention mechanism to effectively select neighboring nodes during the AOI formation. And also, to ensure robust learning, we use double deep Q networks, DDQ, which reduce the overestimation bias inherent in the traditional Q learning methods. It is used to enhance the model stability and effectiveness. Okay, let me introduce some experiments results. Our experiments use a substantial logistic data sets from Cainiao network, consisting of 260,000 orders and 55 million trajectory points spanning 3 months. We compare our methods with 6 baselines. These 6 baselines cover the most basic methods and the most recent models. In this table, we report the performance of the baselines and our methods. We use the metric of trajectory modularity, predictability, and the overall objective we defined before. This table shows that our method significantly outperforms the baseline methods and achieving superior scores in both trajectory modularity and the predictability. Also, the overall objective. Okay. We also conduct ablation study. This figure shows the ablation study result. This component analysis confirms the importance of both the GCN encoder and the attention mechanism. Removing these components individually results in noticeable performance declines. As you can see, the GCN effectively integrates information from the item region graph and plays a role in the model's decision-making process. Also, the attention module makes select important nodes more effectively, and this is our ablation study. Also, at last, we conduct the visualization experiment. We visualize the AOI segmentation results in one region of Shanghai to give an intuitive comparison between different methods. These figures show the results, and each color in these figures, each color represents a different AOI. And the figure A, the first figure shows the geographical information of the target region, and the figure B is the trajectory distribution, and figure C is the package distribution, where the red color indicates high density. And in figure D, the grid generates AOI with a fixed shape, resulting in a poor performance in geographic semantics. And also in the figure E, the road network produces the AOI segmentation results with good spatial semantic meaning. But the fine-grained road network will generate overall small regions that are unnecessary for logistics management and lack service semantic meaning. And also, the last two pictures, the figure I, the region gen is designed to improve the predictability of AOIs. Therefore, a large portion of its generated AOI has a high ACF. However, these regions with dense trajectory transitions are separated since it cannot take the trajectory distribution into account. And the last picture is the visualization result of our method. Our proposed method generates AOI segmentation results considering both package distribution and the trajectory distribution. So it lead to a promising performance in trajectory modularity and the predictability. Okay. And okay, overall, just our method effectively addresses the limitations of existing AOI segmentation methods. And also our experiments and the practical deployment confirm its significant advantages and adaptability. So this is my presentation. Thanks for your time and your attention.
Okay, thanks, Xiao, for presenting this paper. Since the original order is not here, so if you have a question, please drop an email maybe to the original order. Okay, thank you.
Thank you very much.
Okay, hello everyone. I'm Zheng Yangzhou from University of Science and Technology of China. And on behalf of our first author, Kuo Yang, and I will provide this presentation on unveiling concept shift issue via spatial-temporal state learning. 下一页是
Yeah, just click here.
Okay.
Or use the
Okay, I will skip some background of spatial temporal learning, and I will provide the main observation of our research. The current models usually fail to handle the concept shift issue. What is the concept shift issue? It reveals that similar historical observations usually lead to different future observations. For example, the first is F mapping, and it will change to G mapping in other samples or across different samples. So our question is it truly difficult to address? By the research, by our investigation on recent literature, we observe that existing models suffer a performance drop up to 50% on samples exhibiting concept shift issue. So the next question is, does it frequently appear in real-world data sets? So we have illustrated the statistics on the YEP dataset and SD dataset, and we observe that it reached this concept shift issue is reached as high as 24.3% and 32%, nearly 103% or 103 proportion samples will encounter a concept shift issue. So then we will provide some understanding of the concept issue from the perspective of state space. So by a deep investigation, why do the same input X will have different mappings? In our understanding that we argue that the latent states, or such as weather conditions or weather information or some temporal information that are considered as environmental variables will implicitly influence the evolutionary process. So we will attribute such concept issue to the environmental variables. Then Then our question is how to comprehensively model such environmental variables. The answer is unified modeling of the state space. That is to say, we will utilize the environmental variables to unify modeling the state space, and then exploit the state space to the enhanced representation and the future evolutionary process. Then, what's the advantage of the such state space? So some recent literature such as MABA has demonstrated that it can enable the efficient long-range dependency modeling, and the state can carry the rich semantics and provides a natural foundation for unifying the environment information that drives concept shift issue. So by above observations, we provide our overall framework. It consists of three parts. The first is hierarchical state learning, and the second part is prefix, suffix, spatial-temporal state learning, and the third one is the scape collection for spatial-temporal prediction. For the first and the second one, it can enhance the state representation, and for the third one, we introduce a new path to model the state space. Okay, for the first part of the technical details, the hierarchical state learning objective, we utilize a prefix and a suffix representation learning, and it will divide the whole historical observation into the finer granularity to capture more subtle and informative state representation. That's to say that we will capture the previous one and the future one in a hierarchical manner and into different granularities, temporal granularities to capture more informative information. And the second one is the prefix suffix spatial temporal state learning. We will utilize the attention mechanism. We will utilize the attention mechanism to capture the previous one and the latter one. And then for the more details, we just implement this part into 3 steps. First, we will conduct the spatial encoding of the graph, and then we get the representation, first the representation, and next we implement the bidirectional mixing of local steps through a messaging passing kernel, and we can respectively achieve the prefix representation and the suffix representation. And finally, we will perform a global state update based on the local mixed information. And then we will impose a fusion mechanism to fuse the prefix and suffix representation altogether. And finally, we will introduce a scape collection for spatial temporal prediction. In this part, we introduce a collaborative inference path, and we attribute the predicted y into 2 paths for x, e, y, and x and e jointly contribute to y. So the 2 paths is imitated by our framework for the first path and the second path. Okay, then we will derive the prediction y. Then this is our overall framework of state-driven environment inference framework. Then in our experiment part, we will ask 4 questions, and we will answer these 4 questions by ourselves. First is that our proposed framework demonstrates the competitiveness compared to existing state-of-art methods on real-world datasets. And the second one is, does our approach effectively tackle the issue of concept shift? And the third one is, does each component in our framework effectively enhance the generalization capacity? And the last one is our framework running with efficiency? Okay, we implement the experiments on 7 datasets, and 3 of them are social network datasets for link prediction, and the 4 of them are traffic datasets, and 2 of them are retrieved from the large ST dataset. And we comprehensively evaluated the performance of salmon across the 7 river datasets, and we find that our proposal will have outperformed all baselines on social link prediction, and also outperform all baselines on our traffic flow prediction tasks. And for detailed concept shift evaluation, we also implement our experiments on the raw dataset as well as the concept shift dataset. So the salmon exhibits the least performance degradation, and it reveals the least degradation of performance on the samples with concept shift and significantly outperform all existing methods. And the way to disentangle the effectiveness of each component, we also implement the Blanchard study. Our framework consists of 3 subcomponents: prefix suffix representation and hierarchical sequence learning and the skill collection. We blend them into the variance, ablative variance, and show significant performance drop of them. For training efficiency, we also empirically investigate the training efficiency, that is the learning speed of salmon. The training efficiency of our method is compatible with existing approaches. Yes, we illustrate the learning speed. The right is a second per epoch, and we illustrate the 3 datasets and against the 2 baselines, two best baselines. Yes. For conclusion, we can conclude that by comprehensive evaluation and theoretical analysis, our state-driven environment inference can effectively elevate the performance degradation caused by concept shift. And the prefix suffix collaborative state learning can enable capturing richer environmental variables and more fine-grained semantic information. However, there also exist some limitations due to the state space is a latent variable, so we cannot verify how exactly the variable, how the exact ground truth match with the latent variable, match with the state space. So the more interpretability of our approach and of this research is going to be further investigated. Yes, that's all for our presentation. If you have any question, please email the author directly. Yes. Okay. Thank you.
Okay. So any questions?
On page 12, where you present the action studies, what's the selective sample? Is that the concept-driven subset? The one.
Okay. The first is the overall data set, and the second one is the select samples with concept shift.
Okay, thank you.
I also have a quick question regarding the last page. Yeah, you mentioned maybe the ground truth of the environments are not available, right? So can we just maybe doing some clustering over the final results, and then we can take a look over the clustering results, and then maybe analyze some semantics from such clusters? Yeah.
Yes, it's a good insight. We can cluster the samples or cluster the representation in the data space and assign the clustering with some interpretable factors. Yes. Yes, it's a good insight. We can complete this research in the future. Yeah.
Oh,
okay. Thank you.
Thank you. Okay. Yeah. So due to the time limits, we have moved the last talk to this afternoon. So if you are interested so you can join our afternoon session. Okay. Thank you for attending the morning session, and we're looking forward to seeing you this afternoon. Yeah. Okay. And for this afternoon, we still have 2 keynote speech together with some full and short paper presentation. Yeah.